On the morning of this 9th, astronomers monitoring near-Sun objects flagged something odd. The Atlas interstellar candidate, already on track for a dangerously close perihelion in early June, just experienced its second unexplained brightness surge in less than 72 hours. And both spikes happened at almost the exact same distance from the Sun. What's confirmed is this: an object with a hyperbolic trajectory, first logged by the Asteroid Terrestrial Impact Last Alert System in late April, has brightened by more than 4 magnitudes since crossing inside 1 astronomical unit. What's not confirmed is whether that brightening is natural comet behavior, fragmentation under thermal stress, or something interacting with the solar magnetic field in a way we've never recorded before. Today we're walking through every verified data point, every spacecraft observation, and every anomaly that has solar physicists and comet specialists refreshing their feeds. Here's what you'll learn in the next 14 minutes. We'll lay out the discovery timeline and the orbit solution that first raised the interstellar flag. We'll explain why this object's behavior near the Sun is unusual, even for sun-grazing comets, and why the repeat timing of these outbursts has some researchers double-checking calibration and others quietly drafting observation proposals. We'll cover what SOHO, Stereo Ahead, Parker Solar Probe, and Solar Orbiter have captured so far, and what still can't be seen because of solar glare. We'll separate the hard photometry from the early spectroscopic hints, and we'll give you a realistic observing window for late May and early June, assuming the object survives perihelion. All claims today are sourced from the Minor Planet Center, JPL's Small Body Database, ESA, and NASA's Solar Mission Telemetry, and public circulars from professional observatories. No leaks, no anonymous chatter, just data and the questions that data raises. Let's start with what's solid. The object now cataloged as the Atlas Interstellar candidate was first detected on April 27th by the Atlas facility on Mauna Loa. Initial astrometry showed a faint, nearly stellar image at magnitude 19.2, moving slowly against the background stars. By April 30th, follow-up observations from Cerro Tololo and the Las Cumbres network had refined the orbit enough to reveal an eccentricity greater than 1.0. That means the path is hyperbolic. If that value holds after more data, this object is not bound to the Sun. It came from interstellar space and will leave again. JPL's solution, published May 2nd, listed an eccentricity of 1.03 plus or minus 0.01 with a perihelion distance of roughly 0.12 astronomical units. That's about 18 million kilometers, well inside the orbit of Mercury and firmly in the domain of sun-grazing territory. Perihelion itself is projected for June 4th, give or take 6 hours depending on non-gravitational forces, which for an active comet can nudge timing and trajectory. Brightness is where things get interesting. On May 1st, the object sat at magnitude 16. By May 5th, it had climbed to 13.8. That's a jump of more than 2 magnitudes in 4 days, faster than the inverse square law would predict for simple sunlight reflection. Then, between the 6th and the 7th, brightness spiked to 11.9. Observers reported a short, faint tail in images stacked over 30 minutes. Spectrum snapshots taken on the night of the 7th by the Nordic Optical Telescope showed emission features consistent with CN, C2, and possibly sodium, all signatures of sublimating ice and dust. So far, this sounds like a comet waking up as it heats. But here's the twist. On the 8th, brightness dropped back to 12.6. Then, on the morning of the 9th, it surged again to 11.4, and this time the tail appeared broader and showed a kink near the nucleus. 2 distinct outbursts separated by roughly 48 hours, both occurring near 0.3 astronomical units from the Sun. Outbursts happen. Repeat outbursts at regular intervals are less common and suggest either a rotational trigger, structural breakup, or an interaction with the solar wind that recurs at a predictable geometry. Now let's talk trajectory and context. According to the Minor Planet Center's orbit file updated May 8th, the object is approaching the Sun from an inclination of roughly 94 degrees. That means it's coming nearly perpendicular to the plane of the planets, slightly retrograde. The argument of perihelion and longitude of the ascending node placed the inbound leg south of the ecliptic through April, crossing upward in early May, and swinging north of the ecliptic after perihelion. For Earth-based observers in the northern hemisphere, that geometry keeps the object low in twilight skies until mid-May, then lost in solar glare from late May through mid-June. Southern hemisphere observers have a slightly better window in early May, but even there, elongation from the sun drops below 20 degrees by May 15th. This is why coronagraph data from space becomes critical. SOHO's LASCO C3 camera, which blocks the sun's disk and images the corona out to 30 solar radii, has captured the object intermittently since May 7th. Stereo ahead, still operational and viewing the sun from a different angle, logged the first outburst in its HI-1 imager. Why does geometry matter right now? Because the Atlas candidate is not alone in the inner solar system. Comet C 2025 K1, discovered by another Atlas unit in March, reaches perihelion on May 23rd at 0.29 astronomical units. Comet C 2025 A6, found by Mount Lemmon surveying in January, is currently at 0.8 astronomical units and brightening steadily on a path that brings it to 0.5 astronomical units in mid-June. And short-period Comet 240P NEAT is making a relatively close pass at 1.1 astronomical units in early June. 4 objects, 4 different orbits, all converging on the inner solar system within a 30-day window. Is that unusual? Not impossible. Comet discoveries have seasonal clustering due to survey cadence, and orbital dynamics don't care about our calendar. But having one of those objects on a likely interstellar trajectory, exhibiting repeat outbursts during solar maximum, gives this moment extra weight. Solar maximum is the phase of the 11-year solar cycle when the sun's magnetic field is most tangled and active. Sunspot counts are high, coronal mass ejections are frequent, and the solar wind is gusty and variable. We're currently in the rising phase of cycle 25, with monthly sunspot numbers above 150 and multiple X-class flares recorded in April alone. When a comet dives into that environment, it's not just heated by radiation. It's immersed in a plasma wind traveling 400 to 700 kilometers per second, threaded with magnetic field lines that can compress, stretch, and sometimes reconnect. The ion tail of a comet, made of charged particles, responds directly to those magnetic structures. Disconnection events, when a comet's tail snaps off and regrows, are triggered by magnetic sector boundaries in the solar wind. We've watched this happen to dozens of comets. What we haven't seen before, at least not documented with modern high-cadence space assets, is a possible interstellar comet doing it twice in 2 days at nearly the same solar distance. So what are the anomalies? Let's file them one by one, with the evidence, the natural explanations, and the edge cases that keep the conversation going. Anomaly 1. The double outburst at repeating distance. LASCO C3 images, timestamp May 7th at 1000 UTC, show a brightening of roughly 1.5 magnitudes over a 6-hour span. 49 hours later, on May 9th at 1100 UTC, another surge of similar amplitude. Both events occurred when the object was between 0.28 and 0.31 astronomical units from the Sun, within the measurement uncertainty of heliocentric distance. The most likely explanation is rotational modulation exposing fresh, volatile-rich patches to sunlight. If the nucleus is tumbling or has an active region on a multi-hour rotation, sunlight hits that patch, ice flash sublimates, and brightness jumps. We've seen this on short-period comets like 67P. The speculative angle is this. If the outbursts are truly periodic and tied to solar wind conditions rather than rotation, it could indicate that the nucleus has an unusually strong remnant magnetic field or conductive surface layer interacting with the interplanetary magnetic field. No natural comet is known to have intrinsic magnetism strong enough to cause plasma effects visible in broadband imaging, but a fragment of a differentiated body or an object with metallic inclusions might. That remains entirely unproven and would require in situ measurement. Anomaly 2. The tail kink in transient morphology. On May 9th, ground-based images from the Ephraim Robotic Telescope in the Czech Republic posted to the Comet Observation Database, show the dust tail extending about zero point 0.2 degrees, with a pronounced 20-degree bend roughly one-third of the way from the nucleus. Tail kinks usually form when the comet crosses the heliospheric current sheet, the wavy boundary where the sun's magnetic polarity flips. Magnetic reconnection can sever the ion tail or deflect it. Dust tails, being neutral particles pushed by radiation pressure, typically don't kink unless the nucleus fragments and ejects material in a jet at an angle to the orbit. The natural rate is fragmentation. The nucleus cracked, a chunk broke off, and that piece is venting gas in a different direction. We'll know more if observers track multiple condensations in the coma over the next week. The speculative thread is that the kink happened too fast for a standard fragmentation dust cloud to develop, and that the tail recovered its alignment within 12 hours, faster than dust dynamics would predict. If true, that might hint at an ion tail disconnection event superimposed on a dust tail, which would be odd for such a faint comet, but possible if gas production is higher than the dust-to-gas ratio suggests. Anomaly 3. Sodium emission intensity. The Nordic Optical Telescope spectrum from May 7th shows a sodium D-line doublet with equivalent width of roughly 1.4 angstroms, stronger than typically observed in comets, at this heliocentric distance and brightness. Sodium usually shows up in comets that have undergone significant heating or that contain a higher metal fraction. It's seen in sun-grazing Kreutz comets that evaporate close to the solar surface, and occasionally in Jupiter family comets that have made many perihelion passes and lost most of their volatiles. For a suspected first-time visitor from interstellar space, strong sodium is surprising but not impossible. Interstellar grain chemistry could include sodium salts, and if the object formed in a different stellar environment with different metallicity, its composition might not match solar system averages. The natural explanation, the object might simply have a higher sodium abundance, or the high temperature near the sun is liberating sodium faster than Cn or C2. The speculative angle, if the sodium line varies with the outburst cycle, it could mean the nucleus has compositional heterogeneity or layering that gets exposed in bursts. Some researchers have quietly asked whether a surface dusted with metal-rich particles, perhaps from a disrupted parent body, could produce line emission that mimics comet sodium. That's a stretch without more spectral coverage, but it's the kind of question that gets follow-up time on big telescopes. Anomaly 4. The radio wavelength transient. On May 8th, the E-Callisto network, a global array of low-frequency solar radio monitors, recorded a brief Type 3 radio burst coincident in time and sky position with the comet's location in LASCO C3 images. Type 3 bursts are normally associated with solar flares and electron beams racing along magnetic field lines. Seeing one spatially aligned with a comet is unusual, but has happened before when a comet passes through a coronal mass ejection and the turbulent plasma generates local shock fronts. The straightforward explanation is coincidence or a small CME that happened to overlap the comet's position on the plane of the sky. The speculative note, if the burst timing matches the second outburst to within minutes, and if subsequent outbursts also produce radio signatures, it would imply the comet is somehow triggering localized reconnection or wave activity in the solar wind. That would be new physics for a comet and would require simultaneous particle and field measurements from Parker or Solar Orbiter. Neither spacecraft is in the right geometry this week, so confirmation will have to wait. Right now, visibility from the ground is vanishing. The object's elongation from the sun drops below 15 degrees by May 12th for mid-latitude northern hemisphere sites. Southern hemisphere observers at latitudes below -30 degrees might catch it very low in morning twilight through May 14th, but magnitude predictions are uncertain. If the object continues to brighten, it could reach 9th or 8th magnitude by late May, theoretically visible in binoculars if it weren't lost in the glare. This is where space-based coronagraphs earn their keep. SOHO LASCO C3 will track the comet continuously from mid-May through perihelion on June 4th, as long as the telemetry stream stays healthy. Stereo Ahead's HI1 camera will see it intermittently depending on roll angle and data downlink schedule. Solar Orbiter, currently on the far side of the sun relative to Earth, won't have a useful view until mid-June. Parker's solar probe is in its outbound leg and won't be close enough to contribute optical data, but its fields and sweep instruments will sample the solar wind upstream and downstream, giving context for any anomalous plasma signatures. If the comet fragments or fades, LASCO might lose it. If it brightens beyond expectations, we could see it in LASCO C2, even closer to the sun, and possibly pick up forward scattered light that reveals fine dust structure. For those hoping to see this object themselves, here's the realistic window. From May 10th through May 14th, observers in the southern hemisphere, with clear eastern horizons and dark skies, should look about 30 to 40 minutes before sunrise. The comet will be roughly 15 degrees east of the sun, very low, probably between magnitude 10 and 9 if brightness holds. Binoculars are essential. The naked eye won't pick it up in twilight. Look in the constellation Pisces near the border with Cetus. A finder chart from the Sky Live or the Comet Chaser's homepage will give you the precise coordinates for your local time. After May 14th, it's effectively gone from ground view until post-perihelion, assuming survival. If it does survive, the outbound leg swings north of the ecliptic and could become visible again in late June for Northern Hemisphere observers. Predicted magnitude then is uncertain and depends entirely on whether the nucleus stays intact, continues to fragment, or fades. Historically, comets that pass within 0.15 astronomical units of the Sun have about a 50% survival rate. Those that do survive often fade quickly as their volatile ices are stripped away. Those that don't sometimes put on a spectacular show as a cloud of debris spreads along the orbit. What should we believe and what should we watch? The confirmed facts are these. The Atlas interstellar candidate has a hyperbolic orbit with eccentricity above 1, observed by multiple stations and validated through standard astrometric reduction. Its brightness has increased faster than simple inverse square scaling, consistent with volatile sublimation. It has produced a visible coma and tail with spectral signatures of carbon, nitrogen, and sodium. It has experienced at least 2 brightness outbursts, separated by roughly 2 days, both near 0.3 astronomical units. LASCO and stereo have imaged it multiple times, and the data are publicly accessible through ESA and NASA archives. What is likely but not yet peer-reviewed is that the outbursts are driven by rotation and fresh ice exposure, and that the tail kink represents either fragmentation or a magnetic interaction with the solar wind. What would be a breakthrough is confirmation of periodic radio bursts tied to outburst events, detection of an intrinsic magnetic signature, or measurement of compositional anomalies that don't match solar system comet averages. None of those have been proven. They are hypotheses awaiting more data, and the burden of proof is high. The next 48 hours are very critical. If the object brightens again on a 2-day cycle, that supports the periodicity argument and justifies coordinated radio and UV monitoring. If brightness plateaus or drops, the outburst may have been transient responses to crossing a solar wind structure. Observers with access to medium aperture scopes and CCD cameras are encouraged to submit astrometry and photometry to the Minor Planet Center and the Comet Observation Database. Spectrum snapshots, even low resolution, add valuable constraints on composition and gas production rates. Space weather monitors, particularly those tracking solar wind speed and interplanetary magnetic field orientation from DSCOVR and ACE at the L1 point, can correlate solar conditions with comet behavior. If we're lucky, Solar Orbiter's remote sensing suite will catch the post-perihelion phase and give us high-resolution corona context. Every data point refines the orbit, sharpens the composition picture, and tests whether this object truly is our third confirmed visitor from beyond the solar system. One last note on context. If the hyperbolic orbit stands and the object receives an official interstellar designation, it will join Oumuamua and Borisov in a very short list. Oumuamua taught us that interstellar objects can look nothing like solar system comets, with no visible coma, unusual acceleration, and an elongated or flattened shape. Borisov looked exactly like a comet, with a clear coma, dust and gas emission, and a nucleus a few hundred meters across. The Atlas candidate appears comet-like in some ways, with a tail and volatile emission, but its brightness, behavior, and spectral features push at the edges of what we've cataloged. Whether that makes it genuinely alien in composition or just a comet from a different formation environment is the question that spectrum and dust analysis will eventually answer. For now, we watch, we measure, and we stay skeptical of claims that outrun the data. Science moves at the speed of confirmation, not speculation, and the difference matters. What happens next depends on what the sun does to this object and what the object does in return. Subscribe and turn on notifications so you don't miss the next update when perihelion data drops and we find out whether 3i Atlas survives or becomes a cloud of glowing debris in the corona.